Welcome to this deep dive. Today, we're tackling a really fundamental building block in math and science, the distance formula.
Yeah.
You shared some sources that really unpack this, and our mission is to kind of cut through to the core of what it is, where it comes from, and, well, why it's such a surprisingly powerful tool.
That's right. At its heart, coordinate geometry lets us translate visual geometric ideas into algebraic equations. By giving points, numbers, coordinates, we can suddenly use arithmetic to measure things, like distance.
And analyze relationships between shapes, yeah.
Exactly.
Okay, let's get straight into it then. The core question the sources address first seems simple, right? How do you find the straight line distance between any 2 points on a flat plane? Say, point A at x is y and point B at x is y.
And the elegant solution, detailed in the sources, is the distance formula. What's fascinating is that this isn't just some rule someone made up. It springs directly from, well, probably the most famous theorem in geometry.
Ah, Pythagoras. Good old A plus B plus the Z.
The very one.
So how does a theorem about right triangles give us distance on a coordinate plane? That seems like a bit of a jump.
Well, imagine drawing a right-angled triangle. Your 2 points, A and B, they're vertices.
Okay.
And the third vertex, let's call it C, you place it cleverly at x, 0, y.
Ah, so it lines up horizontally with one point and vertically with the other.
Precisely. So the horizontal side of this triangle, its length is just the difference in the x values, the absolute value of x zeros.
Right.
And the vertical side, same idea. The length is the absolute value of y, way, the difference in the y values.
And the distance we actually want, A to B, that's the hypotenuse of this triangle we've just drawn.
Exactly. So apply Pythagoras. The square of the distance, our hypotenuse C, equals the square of the horizontal side, A, plus the square of the vertical side, B.
So distance squared, x plus year 1, which means the distance itself is just the square root of that whole thing. Distance AB, as by 2 by 1, 2, plus y2 dash y1, it's surprisingly clean.
It really is.
Yeah.
And a neat practical thing the sources mention is because you're squaring those differences.
Oh, right. The negative signs disappear.
Exactly. So by 2 by 1, 2 is actually the same as by 1 by 2, 2, 10. It means it doesn't matter which point you call 1 and which you call 2.
That makes sense. The distance from A to B has to be the same as from B to A.
You get the same answer either way.
Okay, let's run through one of the examples from the sources, see it working. How about finding the distance between 3, 6, and 0, 2?
Okay, sure. If we take 3, 6 as our first point, x year way 2 is the second, x years are 2. We plug them in.
Right.
So 32 plus 2, 6.
Okay, so that's Sears 3, 2 plus 16, 12.
Which is square root of 25, which is 5.
Yep. The distance is 5 units. Simple as that.
See, straightforward calculation, really useful result. There's one specific case the sources show that simplifies really nicely. Finding the distance of any point, x, y, from the origin 0.
Right, because if you plug in 0, 0 as, say, x, euro, y...
Then you get 0, 2 plus y, 0, 2. Which just becomes squared by 2 plus y2. Very handy.
Yes, super useful. Like that other example, finding the distance between the origin and negative 12, 5.
Okay.
That's just squared over 2 plus 52. So squared over with 144 dollars plus $25.
Which is squared with 115?
And that comes out to 13.
13. It's a direct application. You see how this one formula, born from Pythagoras, just sort of unlocks a lot in coordinate geometry.
It seems almost too simple for how much it apparently enables. Like, what are some of the bigger things the sources said this allows us to do?
Well, once you can reliably find the distance between any 2 points, you can start defining things. Proving properties of shapes, understanding how points relate to each other.
Like figuring out if points are, like, lined up, collinear.
Exactly that. You can check if 3 points are collinear. Just calculate the distances between all 3 pairs.
Okay.
If the 2 shorter distances add up perfectly to the longest distance, say AB plus BC equals AC.
Then they have to be on the same straight line.
Yep. The distance calculation proves it. And it works for shapes too. Triangles, quadrilaterals. Calculate the side lengths using the formula.
And the diagonal lengths too, I guess.
Yes, sides and diagonals. And those lengths tell you what kind of shape it is. If 2 sides of a triangle are equal,
Isosceles.
all 3 equal.
Equilateral.
Side squared fit Pythagoras.
Right-angled triangle. You can prove it just from the coordinates in this formula.
That's the bridge right there. Algebra giving you proof about geometry.
Wow.
It even lets you find special points, like the circumcenter of a triangle mentioned in the sources.
What's that again?
It's a single point that's the exact same distance from all 3 vertices as the triangle.
So equidistant from all 3 corners.
Yeah.
Okay, so let's wrap this up. The distance formula, it's clearly fundamental, comes straight from Pythagoras, gives us this algebraic handle on geometric distance.
It really is a cornerstone concept, foundational for so many problems.
And thinking about that circumcenter idea, it's kind of wild. How can this simple idea, just finding the distance between 2 points, let you pinpoint a single spot that's perfectly the same distance from 3 completely different points? Defining the center of a circle that hits all 3. That's quite a leap from just measuring one line segment.
It shows you the power embedded in that simple calculation.